The third course was by a man called Steen, and then he described Gödel's theorem. I had been worrying a bit about Gödel's theorem. I'd heard about it, but I didn't quite like the idea because it seemed to say there were things in mathematics you couldn't prove. And I was a little bit worried by that. Anyway, so I went to this course, and what I learned was something very different. And it's if you have a system of rules which you could use to prove some theorem, and if those rules are such that you could put them on a computer, and it can tell you, you try this theorem and you see, is it true or not? You put suggest that this set of rules that can be applied, and the computer chugs through and says, yes, it's been correctly applied, and therefore the thing is true. And you have to believe that the rules do give you truths. That's part of the story. I mean, that's the point of them, after all. So you've looked at them each individually, and you said, does that really, do you believe that one? Yeah, that's okay. What about that one? Yep. What about that? Oh, yeah, I see. That's okay. So
Yep.
that sort of thing.
Yeah.
And that's the sort of rules you would use to prove. These are all statements about infinite numbers of things.
Mm-hmm.
Like if you add two even numbers, you get another even number.
Right. Okay.
That's a statement
Yeah.
about an infinite number of things, yet you can prove it in a couple of steps. And using these rules, that would be very easy to prove. Okay, what Gödel does, as Steen described, and it's very clever, how you can make a statement which, when you look at how it's constructed, it really can be interpreted as saying, I am not provable by those rules.
Right.
So then you say, well, okay, maybe it's false, in which case it is provable by the rules. And since you've built up a trust that these rules really do only give you truths, then you know it must actually be true that it's not provable by the rules, and the statement is true.
Yeah.
So this is and it's a statement which is really about numbers, ordinary numbers. And it's a statement which you can see by virtue of that's the thing that I found stunning. By virtue of your belief that the rules only give you truths, you can see that this is true. Nevertheless, it cannot be proved using the rules.
Right.
So it tells that these rules, whatever they are, cannot encapsulate one's entire way of proving things in mathematics. And I found that absolutely amazing, because it seemed to me that our understanding transcends any kind of rules. But it did strike me as rather remarkable that by our understanding of what the rules are saying enables us to transcend the rules. And this struck me as completely amazing. That somehow the understanding that one has isn't following the rules, there's something beyond that. And this transcending of these rules is a feature of our understanding.
Right.
So it seems to me that whatever understanding is, and I don't know what it is, is some quality that we have which enables us to transcend any set of rules that you have for proving things in mathematics, and they're not enough.
Yeah.
But you can see by understanding them, you can go beyond them. Now, what does understanding involve? Well, it certainly involves consciousness in the normal usage of the words.
Yeah.
Because one says, to understand, you couldn't imagine something understanding a thing if it wasn't even aware of it.
Yes.
So being aware of something is a necessary ingredient. I mean, people complain to me, say, well, you're only talking about a very limited thing. Well, of course it is. But the point is, if what I'm saying has relevance to our understanding, it may not be relevant to all features of understanding. Sure, I'm quite happy with that. But nevertheless, it seems to indicate there's something outside computation in human understanding. And then I start talking about the evolution of how it can happen and how this. It's a feature of general understanding. It's not a very specific thing that mathematicians involve. So then I began thinking, okay, well, what kind of. I mean, I'm a physicalist, so I believe what's going in our heads is obeying the same laws of physics which is going on around us. There's something special injected into our heads which gives us a quality which is beyond the laws of physics. I'm a physicalist. I believe it's the same physics in here as out there and everywhere.
Yeah.
Maybe different parts of it are emphasized in different ways. So I began to think about what are the laws of physics as we know them or knew them at the time. I was thinking about this. Okay, well, Newtonian mechanics, you can put that on a computer. There's a little bit of a catch, which I always worried about a little, but I don't think it's the real answer. The catch is that all these laws of physics depend on the continuum. So you're really talking about properties of real numbers.
Right.
And real numbers are not things you quite put on the computer. You put approximations to them. Now, is there a catch in the fact that these are only approximations? I don't think that's the answer, but I'm prepared to admit that there's another route one might try to follow.
Right, okay.
I'm not following that route because I think the computers are impressive enough. You can get approximation as close as you like, and so I don't think that's the answer. But I'm prepared to look at some suggestion which goes in the other direction. Okay, then I think about, Newtonian mechanics, I think about Maxwell's electrodynamics.
Yep.
You put all those things on the computer. I would think about Einstein's general relativity. I knew that was pretty hard at the time. They haven't got very far. But nowadays, you can talk about spiraling black holes, and it's really very, very detailed what people do.
Yeah.
So sure. Then what about quantum mechanics? Well, Schrödinger equation, you can put that on a computer. It has a problem with how many variables you have to, and it sometimes people regard it as a difficult problem for a complicated system. But it's not really fundamentally different. So the Schrödinger equation also. But that's not the whole of quantum mechanics.
No.
Quantum mechanics involves not just the evolution of the quantum state according to the Schrödinger equation, or whatever you like to call it, unitary evolution. It involves measurement. And the measurement problem violates Schrödinger equation. You evolve a state, and it says, if you made a measurement of such and such a type, it would give you a probability of that and a probability of this. If you evolve the measuring device as well as the system, then you get a contradiction, because it says that the answer of the measurement is a superposition of this and that. Schrödinger obviously worried about this with his cat. I mean, that's why he brought the cat into the discussion.
Right.
Really to show that there's something wrong here. There's something in the theory. I mean, people often say, well, maybe with a sufficient technicality we could build a Schrödinger's cat. That was not what Schrödinger's point was. He was saying this is ridiculous.
Yeah.
You can't really have a cat which is dead and alive at the same time.
Yeah, but it was a mere illustration of a wider point, right?
That's right. So Schrödinger, and I'm well in line with Schrödinger's viewpoint on this. Einstein took a rather similar view. In fact, Dirac did too, even though he didn't enunciate that. You have to see what his later. He didn't say much about what he thought about quantum mechanics, but he took a rather similar view. You see, quantum mechanics is incomplete.
Right.
Because it doesn't explain the collapse of the wave function. The Schrödinger equation is a smooth, continuous evolution of the state, but it's not what you get when you make a measurement.
Yeah.
When you make a measurement, which after all is broadening the system a bit to include the measuring apparatus and all that, why doesn't it follow the Schrödinger equation? And that worried Schrödinger very much. And it seems to me this is the gap that's not present in all the other theories. See, all the other theories right up to the point, even including the Schrödinger equation, or the evolution, unitary evolution in quantum mechanics, they are all things you could put on a computer. So where is there something that you couldn't maybe put on a computer? And the argument I was making here is that it's in the collapse of the wave function.
Right.
So there is some process, and I'm not taking the view, as many people did in the early days of quantum mechanics, that it's the conscious observer looking at the system and observing.
Yeah.
That's the sort of terminology which suggests it's that.
Yeah.
Observing the system. No, I don't believe that. It doesn't really work when you think about it in detail. I won't go into that, but it certainly doesn't really work. So I don't believe it's that. However, it's a different role for consciousness, almost the opposite. That whatever consciousness is depends upon what this currently unknown, but we know something about it, which is to do with seeing how general relativity relates to quantum mechanics.
Right.
But it's the other way around. It's not how you quantize general relativity, which is what many of my colleagues try and do.
Right.
It's the opposite. How you gravitize quantum mechanics. You try to put the principle of equivalence, these great principles of Galileo, into the theory and the Einstein way of resolving these principles of Galileo into an overall theory and imposing that on quantum mechanics. And you can see when you look at this that the arguments tell you that with certain mass displacements, that the superposition of it being in one position or another has to go to one or the other in a certain time scale.
Yep.
And that time scale you can estimate.
Yeah.
And so this, I claim, is what's going on in the brain.
Ah,
Where in the brain, I had no idea. I learned a bit of neurophysiology. I just couldn't see where in the brain it could be doing it.
yeah.
I rather sort of petered off in The Emperor's New Mind without knowing the answer. But then Stuart Hameroff, who was an anesthesiologist in Tucson in Arizona,
Yeah.
and he wrote to me and said, more or less, evidently you don't know about microtubules. He didn't put it quite like that.
Yeah.
But he suggested there's something. I mean, he was very interested in general anesthesia, and he realized that it's not a chemistry question. I mean, how you turn it off is a route into what it is. And what turns it off is not chemistry, because you have many, many substances completely unrelated chemically, which are general anesthetics. One of the most striking being xenon, which is an inert gas, or more or less inert. And so it's not chemical processes, it's some physical process. And, well, we developed these ideas together, going off on different routes and trying to come back again all the time, and formulating a scheme which is referred to as the OR proposal.
Yeah.
ORC means orchestrated. It's not the OR means objective reduction. So the reduction means the collapse of the wave function. Objective means it really is a physical process. And then there are curious features about when it happens, which is another whole story.
Which is another question entirely.
Yes, it's got very interesting. Going back to experiments which I do describe in The Emperor's New Mind, due to Benjamin Libet. And there's some renewed interest in these things.
You've already mentioned, for example, that you were taught by Dirac. Well, I mean, maybe that takes us to a question of how it is that you approach the work that you do. So you've said in the past that you're quite a visual thinker.
Yeah.
What is, I mean, so from everything from Penrose tiling all the way through to, CCC, views on cosmology, views, questions about human consciousness. What is the unifying theme of being a visual thinker? How does that feature in the way you do your work?
It certainly is an important element to my thinking. And I remember when I was at school, I sort of thought I was better than most of my colleagues at mathematics. And then I thought, well, I feel like a bit of an oddball. And when I go to university, I will find people who think like me. That was not true.
Right.
What I found was there were more different ways of thinking about mathematics than I'd ever encountered before. But the main division, clearly, was whether you tended to think visually or in terms of equations.
Right.
And I was clearly one of the fairly small fraction of the class who was definitely a visual person.
Right.
It didn't do me too well in a sense, because at University College they had this way of doing the maths that to the first 2 years you actually took the main exam at the end of 2 years. It was a 3-year course, and the third year was to do your special topics.
Okay.
Now, in my third year, I specialized in the 2 geometry topics.
Right.
But when I learnt later how well I did, my geometry papers were not my best paper. The reason was that in algebra, it's easy because you can, I don't know if it's the real answer, but it's something like always you're using one side of the brain rather than crossing over from one to the other. I don't know if it's as simple as that.
Right.
But with doing the geometry papers, I can see how to do the problem. Then I have to translate that into words, write it out in words, and then do it again. So it's all this going from one to the other and one to the other. And I was a slow writer, and I didn't finish the papers. Whereas in algebra, you can see it, so you don't have to switch around in that way. This is the problem, this is the answer. And you just go like this. And so I did much better in my algebra paper than I did in geometry. But Galileo, I always had a feeling, I don't know if it was, how much of it was his trouble with the church and all that, and trying to battle the current views. But there were so many things which he understood, which people didn't. And the principle of equivalence. And I like the one with the fireworks. He imagines the fireworks, and they make this beautiful sphere of sparks, and it drops, and it remains a sphere as it drops. You can cancel out gravity by falling freely. I mean, these beautiful principles that really so fundamental to physics, and this coupled with his fight against the authoritarian role of the church and I think that a lot of that was why he was my particular hero.